I'm really excited to be giving this talk. It's about something I implemented about 2 years ago. And I submitted it, I wrote this talk proposal originally for C++ Now 2025. And I was really disappointed when C++ Now last year, they accepted one of my more boring talks that actually teaches people something useful instead. But luckily I get the chance to present it again. I remember when I implemented some of this, I was like skeptical whether I'm not going too far at this point. And my boss was like, no, just keep going. And even if it fails, it's going to make a great C++ Now talk. So really excited. I also love how it's like scheduled in parallel to Brett's pragmatic CMake talk, because nothing about this is pragmatic. So before we get going, I work at ThinkSo. We are the world's leading business presentation software. So everybody who does PowerPoint slides for a living uses our plugin. We are over 20 years old, we have over 1 million customers at over 25,000 companies, and like every consultant, every C-level executive in every big company uses our plugin. It seamlessly integrates into PowerPoint and makes it like easier to create slides. We've got custom charts, automatic layout, integration with Excel, all kinds of stuff. This is done by reverse engineering some of Microsoft PowerPoint, so then essentially hack into it. We are really into C++. We are a member of the C++ Standard Foundation, and we are like the leading force behind German's participation in the C++ Standardization Committee. And by leading force, I mean we pay money. And we do everything in C++, which is why we're like so passionate about supporting C++ conferences. So what this talk is about. We're going to implement max a, b. While we're doing it, we're going to embark on a journey of accidental and essential complexity. And we're going to look at the worst C++ features C++ has ever added. So I have I have something in mind. Maybe you think about what's the worst C++ feature there is. So the function we're going to implement is this. The maximum function max a, b returns the greater of the two arguments. Right? How hard can it be? Right? Because like this is this, right? Max function takes two ints, a and b, and it returns the greater of the two ints using an if-else. If this is too much code, you can also use a ternary operator. Now it's only one line, but of course, to be absolutely correct, you also have to do all this. I'm going to ignore the no discard, the const expand the no except for the rest of the talk. So this is max a, b for integers. So the obvious first step is, well, it's for integers, let's make it generic. Right? And that's very easy. Make it a template type in T. I'll put everything by const reference because, like in generic code, it might be expensive to copy or whatever. And hold that. Right? But I will really, as Sean Perrin said in his keynote, like generic programming isn't just programming with generics. You have to ask yourself, what are the type requirements? Don't just write a template. Think about what are the type requirements. And here we both have the syntactic requirements, where T must obviously provide an operator less than that returns something that is contextually convertible to bool. But of course, this isn't enough. Like we also have semantics. This operator less than must mean something. And the thing it means is it implements a strict total order. So this is a math term. So a strict total order is something that is defined on a set S, and it's a binding relation on that set S. So it like relates pairs. And this relation has three properties. The first is the irreflexivity. So A is not less than A for all A in S. The transitivity, so if A is less than B and B is less than C, then it must follow that A is less than C for all possible A, B, and C in S. And finally, we've got something called trichotomy. For all A, B, and S, exactly one of A less than B, A equal to B, and or B less than A is true. So these are the requirements. I've chosen to express them as a comment. I could also use a concept, but like the semantic is a comment anyway, so why not just stick it with a comment? So are we done now? Consider this code. We've got some person, each person has a unique ID, and then they have a name. And then we want to get the maximum by using like a wrapper struct that compares it by name. And we want the person with like the bigger name, so to speak. And if you have code like this, so now we've got two people, both called Jonathan, but different IDs because they're different people. And if you call it, you violated the semantic requirements of a strict total order because the ordering cannot distinguish between the two, but they're not the same. They're like different people. And this is fine. It's just we overspecified the domain, the function. Right? We don't want a strict total order. It's fine if you have a strict weak order. And this is a relaxation of a strict total order. So a strict weak order has 4 properties. It's still irreflexive and it's still transitive, but instead of strict autonomy, we have asymmetry. So if A is less than B, then it must not be the case that B is less than A. And the weaker transitivity of incomparability. So we can say that A is equivalent to B if A is neither less than B nor B is less than A. And it must hold that if A is equivalent to B and B is equivalent to C, then A must be equivalent to C. Right? And in more formal terms, we can say that the strict weak order of S defines the strict total order of the equivalence classes under tilde. And that's not important. Essentially, it means that it's fine if you have a weaker version of equal under the order than the actual equality in our object. So if you only require a strict weak order, which the standard max does, then this code is perfectly fine. The only question is, should the result be P1 or P2? Our ordering does not distinguish between P1 or P2 because it just compares it by name. But we can distinguish in the result, like which person it is. And so what should the maximum be? Should this be P1 or P2? So in our implementation right now, if A and B are like equal, but it doesn't necessarily mean equal, they're just equivalent under our ordering, then A is not less than B. So it follows that we return A. And we could have also implemented it like this, so just swapped it around. And now, if in this case, if we get to give 2 equal options, we could give B. And there's a pretty compelling argument that we should implement the second version, because in some sense, the second argument is bigger than the first argument by definition. So if you have like equal arguments, then return the second one instead of the first one. And then min does the opposite, and then we've got a nice symmetry. But I'm going to stick with the first option because that is what the standard library does.
Which is wrong. Walter Brown had an entire talk about that.
Yes.
Question.
Yeah, I was about to bring him up because I gave this talk at C++ on C last year, and Walter Brown was in the audience. He was in his like mobility scooter in the last one, and at this slide he left. Right, and because it was his mobility scooter, I just saw him scoot away in the background. So yes, arguably this is the second version is correct. More correct, but I did all the slides, so you know, just gonna stick with the first one. And for what's now follows is going to be the least of our worries. So let's try and support mixed comparisons, because right now we can't get the maximum of a string and a string view. And this is simply because we have a single template parameter, so the compiler tries to like substitute t, give it like one type that is either string or string view, and so it just can't deduce them. That, however, is easy to fix. Just give it a second template parameter. So now we've got type name t and type name u, and we change the requirements. Now that they like together need like an operator less than that semantically implements a strict weak order. So even though they're like different types, they should still represent the same thing, so we can like reasonably compare between them and make it all well defined. Now the return type is auto, because like what's the return type? If we don't want it to be auto, we can use a trait. This trait is common type t. So it's the common type between t and u. And it's a really weird type trait if you start digging into it. It's essentially this. So it's essentially a decal type of the ternary operator, but we've got some extra decays in there because we don't want references at any point. And we need a decay on both levels for reasons. There's also a bunch of exceptions. Like if you look at the wording, there's like, if t is this and u is this, then the common type t is, then there's a bunch of exceptions involving like arrays and like I don't want to know. But like essentially it's a decal type of the ternary operator, sufficiently decayed, and then we do some weird stuff about arrays or whatever. But it doesn't stop there because we can like customize it. If we got our custom types, we can say the common type between my type and my other type is this type. And this is really neat. It just does not affect the ternary operator, right? Only because you customize it, the ternary operator still uses like the language definition, and so just because you have said that there's a common type, the ternary operator might not see it, and so just not compile. So that's useful, I guess.
Would defining a conversion operator to one of the types of the other help with that?
Yeah, if you define a conversion operator, then the ternary operator picks it up, but then you also wouldn't need to like define. I don't know. There's probably some weird edge case. I don't want to know, honestly. It's also variadic, so you can have the common type of like multiple ones in one go, but it's not associative, which is fun. What this means is that we can define types A, B, and C such that the common type of A, B, and C is not the same as the common type of B, C, A. And those types are these ones. So we've got the base class A, and two classes B and C that derive from A. Then if we do the common type of AB with C, that is A. Because the common type of A and B is A, and the common type of A and C is A. But if we do it the other way around, then we first get the common type of B and C, and that one does not exist. Because the rules for common type means it's either one of the types. It's not some unrelated third type that is potentially reachable with some conversion sequence. So that's fun, I guess. But anyways, our definition now works. We can do a string and a string view, and we get world. We can do an int and an unsigned int using -1 and +1, and we get
unsigned backsign.
Yeah, we got up about 4 billion, obviously. I mean, to be fair, 4 billion is bigger than -1 and +1, but it's not quite what we're after. And there are two problems here. The first problem is signed-unsigned comparison. If you compare an int and an unsigned, it can be implemented in 3 ways. We could do the correct thing and compare the mathematical value they represent. This means that negative numbers are less than positive numbers, because that's what math says. We could convert both to ints and then compare the two ints. This means that negative numbers are less than positive numbers, but if the number gets too positive, then it's negative again. Or we could do what C++ does, which is convert both to unsigned, then compare to unsigned. And then negative numbers are suddenly bigger than positive numbers. But even if C++ were to be defined to do the correct thing, which by the way, there's now a function. So if you actually want to compare things in the mathematical way, there's a function you can call that does the correct thing. That doesn't solve it. Because the second problem is the conversion for the return type. So what's the common type of int and unsigned? Well, it could be the next larger signed integer type that can fit both types. And this would be the correct answer. This could fit any possible value. It could be int, in which case we get problems if the number is too big, then we wrap around. So C++ says it's unsigned, and this means that if a negative value, it turns into positive value, so a -1 turns into unix. And now the problem with doing the correct thing is that eventually we're going to run out of bits. Right? If you have an unsigned long and a long, there isn't a type that can fit both values. Okay, there might be an extended type, but then if you go to the extended types, eventually we'll run out of bits. Right? So we at ThinkCell actually say this should be invalid. Right? There should not be a common type between int and unsigned, because there isn't a common type between, in the generic case, between unsigned and signed and unsigned integers, there isn't a common type. So we actually have this trait, which is called safely convertible. And we say that the source is safely convertible to a target. If it is convertible, there's some asterisk, I will get back to that, and that conversion is safe. And it's a bit awkwardly named, because safe is not safe as in memory safe. Safe is just stuff derived to base slicing is not safe, or into unsigned conversion is not safe. Right? It's just conversions you don't want to have happen are not allowed by this concept. And you can specialize some trait to define it for your own class types that we have. But so we handle the built-in types, and then we specialize it for class types. Right? And so we've got TC common type, which is just the safe common type. So it's the same as the std common type, but it's not defined unless all the types are safely convertible to the common type. And so if we specify the return type as TC common type, we can have an int and an unsigned and call it, and this will be a compiler error because there is no TC common type between int and unsigned, because it would involve an unsafe conversion, so to speak. And with that, we correctly handle mixed comparison. Okay, perfect for wording. Right now, we take everything by const tref. And so when we call it refer to strings, the result is going to be a std string, which is an unnecessary copy. Right? Previously, before we did the mixed comparison, the return type was simply const tref. And then this would just return a const tref to a string without an unnecessary copy. So we don't want this copy. So we could just directly say, okay, we return the common type, but if they're the same type, we just return the reference. Right? And that solves the previous problem, because now if you give it the same type twice, you will get a reference. But if you give it two different types, you will get a common type after implicit conversion. Because in general, if you have two different types, you can't return a reference, because one of the types has to be converted into something, and so you can't return a reference to that. you have to return it a PR value. So this is what we do with that. And this works in this sense that when we call it with string and string AB, we get no copy of the result. But if we call it with a const char pointer understood string, rvalue, then we are having two different types. But there's a common type, which is std string, because both are convertible. And we return this std string as the return type. That is all good. The problem is we do it by copying world over. It's an R value it should be moved into. Like we don't want a copy operation, we want a move operation into the return. Like the return type is correct, we just get it the wrong way. Right? And like that's easy enough. Just forward the stuff. Right? So just don't take it by const ref. Take it like by forwarding reference and then forward it in there. And now we just require that the common type exists, but we actually return whatever the type is, including the reference, so return it by decal type out. Right? And now this maybe works. Like what actually happens here? If we like give it like a string lvalue reference and a string rvalue reference, what is the return type of this function? Like what does the turning operator do? And it does this table. So the turning operator, if you have like two types that only differ in like CV ref qualification, this is the behavior of the table. So there are 4 sections. The top left is both are lvalue references, and then the result is always an lvalue reference, and it is const qualified if at least one of the references was const qualified, because otherwise we would like drop the const. Right? So it's at least one. And similar in the bottom right, just for rvalue references. So if both are rvalue references, then the result is an rvalue reference, which is const qualified if at least one is const qualified. And then if you mix an lvalue into an rvalue reference, we simply return t as a PR value. So the result of the turning operator is a PR value when we mix an lvalue into an rvalue reference. This means that in our implementation, when we call it with hello and std string, the result will be correctly moved. The result is a std string, we forward it, we move it into the thing. But if you then go back and have like a string lvalue and a string rvalue, this again creates an unnecessary copy because the result is a PR value. Right? The result of the turning operator is a PR value, even though we like, in this case, it would be like perfectly fine to like return a reference to something, like an R value reference or something, right? Because this what the work, the everything, like the lifetime checks out, right? So this is in some sense an unnecessary copy. And like unnecessary there is in quotation marks, but like, let's say it is unnecessary and we want to like prevent this unnecessary copy by ensuring that in this case, we also return some kind of reference and not a PR value. Luckily, there is a way we can do that because there's also std common reference. And std common reference is sort of the reference equivalent version of std common type. And so if the two types are like the same types modulo CV ref qualification, it figures out some type of the correct CV ref qualification. Otherwise, it will fall back to std common type T. And crucially, it is not a decal type of the turning operator. Because a decal type of the turning operator will give you a PR value, which is not a reference. Whereas the common reference will try and give you a reference, unless it like really can't, because it's like two different types, and then it returns the common type. Right. So the table for common reference looks like this. It's the same in the blue and the green as with the decal type of the turning operator. But if we mix L values and R value references, the result will be const T ref. Right. So if we use that, then we avoid the PR value because we return a const tref. But why does it return a const tref? Well, it returns const tref because of this diagram on the left. So those are the 4 reference types, and the arrows indicate implicit conversion. So a tref is convertible to a const tref, and a tref is convertible to a const tref. And R value references are implicitly convertible to const tref. And so the common reference is const ref because that is sort of the universal receiver. Right? That's the type all references convert to. And then the reference themselves, they bind to something. And the property here is it a temporary or is it const qualified? Right? And so tref does not bind to temporary, does not bind to const. Only the const one binds to const. And only everything except tref binds to a temporary. So if you have a function that doesn't care about the lifetime orientation, you take a const ref because const ref binds to all other kinds of references, and it allows both temporaries and const objects. Right? This is how we design generic code. But like, is that ideal? Right? Like if we had a time machine and like could break codes, like would we have done it this way? And I'd say no, because if we look at this table, we've got a duplication here. Like const ref and const reference, they're both yes, yes. And we're like missing the column that does not bind to temporary, but does allow to const. Right? So I would argue, and like we at Thinkcell would argue, that like ideally it would look like this. And so the sort of the universal type would be const ref as the type that implicitly converts something. And that is the type that allows both temporaries and const, whereas const ref does not allow temporary, it only allows const. Right? So instead of having what's now the role of const ref in this alternative universe would be const ref as the type of the universal receiver, because it indicates that we don't want to mutate it with the const, and it indicates that we are fine with temporaries with the ref. Right? And like we'd argue this is a better word.
Sorry.
Yeah.
Do you mean tref here as a forwarding reference?
No, as an R-value reference.
As an R-value?
Yes.
R-value binds to const. Okay.
Yeah. No, like the const R-value binds to const.
But to normal R-value, const doesn't bind.
Yes.
Okay.
Yes. And like that's not the only thing we would change is prevent const ref from binding to temporaries. Right? And keep the const behavior otherwise the same.
Thank you.
And like this is not possible because at the time const ref was added, we didn't have R-value references, and so C++ went in the direction we had. But like we'd argue this one is more useful because it gives you this extra column in the table. So we like pretend sometimes we live in this world by having TC common reference, which is like common reference, but it behaves differently for mixing L values and R values. Whereas stud common reference gives you a const int ref, we give you a const int ref. Because we pretend that this is the universal receiver, and then also the fallback is to TC common type and not stud common type, so the common reference of like an int and an unsigned still doesn't exist. Right.
So the common reference you wrote there, I don't understand why the const is getting introduced. Why?
So the const is introduced so stud common reference introduces a const because of this chart. Const ref is the only type that is implicitly convertible to both tref and tref. Okay. So if an int ref and an int ref, you get a const ref out because that's the conversion chain. Okay. Right? And what we say is we pretend the conversion chain looks like this, and so we give you a const R-value reference instead of a const L-value reference. Okay. Because at least one of the arguments was an R-value, so we give you an R-value reference instead of saying it's an L-value. Right? That's the difference. That's where the const is coming from. And like we don't if we didn't have the const, then we would silently move from an L-value reference, which is not what we want. Right? We just want to use the R-value to indicate that one of them was an R-value, not to indicate that we can move on. So we make it a const R-value reference. So the table of TC common reference looks like this. Again, the only thing that changes is the red part, and now we return a const ref when mixing L values and R values. Which means that we would implement max like this. So we say max takes our thing, returns a common reference of T and U, the TC common reference, which gives us the type that we want. Except that this code horribly crashes. Yeah.
Do you not need to static cast the ternary?
You're 2 slides ahead. First, this code crashes. This code crashes because the ternary operator gives you a PR value. So even if you were to use stud common reference as the return type, you will get a PR value from the ternary operator, not a reference. So you will get a reference to a PR value created in the return statement. This will immediately dangle. It's really unfortunate that that stud common reference and like ternary operator behave in this way. It's really unfortunate. To fix that, you write an if else, because the if else doesn't include the PR value, and that works. The second thing is, yes, we need a static cast, because we pretend there is an implicit conversion when there isn't an implicit conversion. A tref isn't implicitly convertible to const ref, unfortunately, we'd say. So you have to put in a static cast. This is kind of ugly. So we solve it in the way we solve most of the problems with C++. We have a macro. Conditional R value as ref. Yes?
Yeah, so basically I was also going to ask how are you going to fix this non-existing implicit conversion, but explicit still works, right?
Yeah. So we have a macro, and the macro does this.
Can just, I see.
Yes.
Does const ref also extend lifetime?
Const deref also extends lifetime. Yes. Yeah, I agree.
For sure.
Sure. Yeah. So we have this macro, which does the ternary but cast it to the type we want. And like the actual code uses a static cast and not like the CLI cast, but like it's fine. It's just the only conversion that actually happens with the static cast is the adjustment of an intref into a const intref. Otherwise, it's fine. Yes.
Just to quickly finish the previous topic. Even non-const R-value reference prolongs lifetime.
Really?
Yes, even non-const R-value reference prolongs lifetime.
Yeah.
That's for sure.
Yeah. I think all references prolong lifetime. They're not all.
When you can bind temporaries.
Yeah. And so the name of the macro is rvalues ref. We also have rvalues prvalue. If you just want the don't want the rvalues as reference, but as prvalues, that has like a slightly different. But one nice thing about this macro is that we have code like this, which just works. Because now if we specialize TC common reference, this is actually gets picked up by the ternary operator because it does a static cast anyway, right? And we've got some code in there that like works with class hierarchies. And if you specify a base class as a member, we've got some metaprogramming to figure out the like least common ancestors of all the ones and give you the appropriate reference you want in there. And this is like, I don't get the reactions of the audience. This is like really useful. Like when I introduced it, I was able to simplify so much code with like extra casts in there to get the right thing and like.
It's useful, but it's not generic anymore.
I mean, it is generic. You just need, I mean, okay, it's not generic between all class hierarchies. It's generic for the one class hierarchy we have in our code base, which inherits the thing anyway. And like with reflection, you can make it generic. And also like we've got specialization for comment type between like T and nollupt, which gives you an optional T, right? Which is really annoying that this isn't in the ternary operator. So this is like really useful. It just requires a macro instead of the ternary operator. But like if you're already reacting this strongly to this macro, you're not gonna like the rest of the talk. Anyways, fun TMP challenge, like implement that. Like given T and U, find the like most derived common ancestors by like repeatedly walking base. Anyways. So after we did all that, our code, the string L value and the string R value works. It will give you a const string R value reference. You can print it. Everything works. So let's start composing it. So this is max. This is min. Same thing. We just flip it around. And this is clam. So clam takes three things, and then we want the maximum of the value of the lower bound, and then that with the minimum of the upper bound. And so we can call it with three strings, and we clamp it, and everything works. We turn our bounds into string views, and the code crashes. So let's walk through it. So the value is a string reference, and then we've got two L value references to string. The first thing we do is we get the maximum of the string L value reference and the string view L value reference. These are two unrelated types, so the result is a prvalue string view, because that is the common type between a string and a string view. Like both types are convertible to string view. So here we've got a prvalue string view. We then pass that to min together with an L value reference to a string view. But PR values cannot get passed to functions that take forwarding reference. It gets turned into an R value reference, and then we've got the result will be the common reference between an R value reference to string view and an L value reference to string view, which is a const standard string view. R value reference. So what's happening here is we're returning an R value reference to a string view temporary that was created inside the function. And this crashes because we return a reference to something that doesn't open. Now, this is unfortunate, but the interesting question is, whose fault is it? Like who did something wrong? So let me introduce some terminology. So we've got a projection. Projection is a function that returns a reference whose lifetime is tied to one of the arguments, like max and min and clamp. Like they return references like tied to one of the arguments. And like clamp in particular is a composed projection because it's a projection built by composing multiple projections. And the problem we have here is that if a projection returns an R value reference to a PR value argument, composing them can lead to return to dangling references. Because when you compose them, the R value reference to the PR value is just treated as a generic R value reference. You compose them, you return a dangling reference. How to fix it? One way you would say, well, don't do that. A projection never returns an R value reference. Then it can never return an R value reference to a PR value, right? And the problem is just fine. And we could implement max like this. So we've got a type trait decay rvalue, which just decays it if it's an rvalue reference, and otherwise leave it unchanged. And then we implement max like this. And this sidesteps the problem, because now instead of returning an rvalue reference to a potentially PR value, this will be returned as a PR value. And this is a fine solution, but like it's technically too aggressive. Right? Like we would decay it in cases where it's perfectly fine. Like when the rvalue reference, the PR value is like lifetime extended and lives long enough, like this is potentially too aggressive. Right? And like, okay, maybe for max it doesn't matter, but like the actual problem we had in the code base was like trimming, where like trim is implemented as a composition between trim left and trim right, and they try to modify the container in place if necessary, and they don't want to create like unnecessary moves of like big std arrays or something that we passed into for some reason. But yes, in principle, that is a solution. It's just too aggressive, so let's look for another one. So another solution is a projection should never return an rvalue reference to a PR value argument. So we've got some trait, let's say decay of PR value t, and it decays t if any of the arguments is a PR value. And then we implement max by saying, okay, we return the common reference, but like decay it if t or u is a PR value. And this would be a perfectly fine solution. It has just one slight problem. We can't implement it because of the way forwarding references work. So if you have a forwarding reference and you give it with an L value, t will be like an L value reference to the type, and t reference will be also an L value reference. So you end up with an L value reference. If you give it an X value, so like a move or something, t will be u, and t refer will then make it an R value reference. And if you give it a PR value, the same thing. Like t will be whatever the type is, and t refer will be the reference. And this means that like by the time you've called the function, you can no longer distinguish between PR value and X value arguments. Like they all get turned into the same thing. And this is a bit unfortunate because it would have been easily possible to distinguish between them by just tweaking the rules and saying if you get an X value, t gets turned into an R value reference. Then t reference wouldn't change, it's still an R value reference, but by looking at t without the reference, you'd be able to distinguish between X value and PR values, and you could implement this thing. Right? This would have been perfectly fine, like back in C++11. And it would solve this thing, but unfortunately, this isn't what we ended up with, because the whole forwarding reference thing was a hack to begin with, and I guess it wasn't properly explored. But like, even if you implement that, it might not be enough nuance. So if you've got code like this in our clamp, like this is problematic because this is dangling. But if you like take the entire expression and put it in a different context, this is perfectly fine. Because lifetime extension destroys everything at the semicolon, so everything lives long enough to begin with. It's only when we like cross a function boundary that we get into the problem. So it's actually the user of the composed projection that is responsible for preventing dangling references, because it's the one that knows whether, oh, if you got an R value reference to some PR value in an intermediate expression, you should decay it. So the correct solution, I would say, is that a composed projection should never return a reference to an intermediate PR value, which means that like clamp should be implemented like this. We've got this function decay R value, which decays an R value because we return it. So we cannot return an R value out of there. But we can do even better, because this is too aggressive. Like if the R value came from the outside, then we don't need to decay it. So you can say like only decay it if the result of max is a PR value. Because if the result of max is a PR value, we must not return an R value reference to that PR value. And in that case, decay it, otherwise keep it fine. Right? Because if the R value reference comes from the outside and wasn't created by max, then we don't need to decay it. So only in this particular case do we need the decay. Otherwise, this code works perfectly fine, and then we end up with like the least amount of decays necessary to achieve correctness. This is just kind of ugly and error-prone, right? Like remember to do all this. It's kind of ugly and error-prone, and it also does not work if we have some generic composition, right? So this is like a combinator that has three functions, f, g, and h. And essentially it takes two arguments and it transforms t with g and u with h, and then passes the results of both of those to f. Right? And implementing solution 3 means this combinator is responsible for decaying if stuff happens. So, okay, let's say we decay if j or h returns a PR value, right? Because then f might return an R value reference to that. But like, what if f always returns the number, like the number 5 as an null-value reference to some global object or something, like unrelated to the lifetime of any of the arguments? Then we don't need to decay it because f's return type the lifetime isn't tied to any of the arguments to begin with, right? So really, we want to say decay if f returns an R value to a PR value created by GOH. The problem is we don't know that in this generic code because we don't know what FGOH are doing. Like we don't know the lifetime contract of those functions, right? We don't know whether the result of G is a PR value. I mean, we know whether the result of G is a PR value, but then we don't know if f returns an R value reference. Is it because we give it that PR value, or does f just always return an R value reference regardless of what we put in there, right? Like we can't look into it. And at this point, we can use my favorite saying, which is C++ isn't a particularly great language, but all problems in C++ can be fixed with more C++. And in particular, we want to like track the lifetime. So let's introduce a new reference type. A special marker type to indicate this is a reference to a temporary. And we call it TC temporary. It looks like this. So it's essentially a fancy R value reference. So it behaves just like an R value reference. It is constructible from an L value reference with an explicit conversion, and implicitly constructible from regular R value reference. And then it's like implicitly convertible to a reference, and like just like R value references. And if you've got an R value reference that is an L value, that is actually an L value, right? You just have to move it, and only the moved one is the R value. And the idea is that we use this as a marker type to indicate, hey, you are an R value reference to an intermediate PR value, and not just an R value reference that outlives. Yes?
Sorry, is that conversion to operator T ref?
Mm-hmm.
Is it conversion to mutable reference?
Depending on whether T was mutable.
How is the constraint for the second constructor template even possible to satisfy when U is a value type? It can't deduce as an R value reference.
I might have simplified it too much for slide code to fit on the side, but like the idea is this.
Okay.
Yeah. Anyways, so like it's probably not like slide code, but like the idea is this, right? It's a marker type for an R value reference, and so we use it to say, hey, given a type T, wrap it in a TC temporary if it is a PR value that isn't already wrapped in a TC temporary. And then we've got this convenient macro to create this thing. And the reason that it's a macro and not a function is because a function cannot distinguish between PR value and R value reference, like X values, right? It has to be a macro because only the macro has the Jekyll type powers to actually detect PR values versus X values, right? And so this conditionally wraps PR values as temporaries and leaves everything unchanged. And so, for example, if we give it an object, which is an L value, the result will be an L value reference. If you move something in, the result will be an R value reference, because this is not a reference to a PR value. If you give it a PR value, you will get a TC temporary. If you call a function that returns a PR value, you will get a TC temporary. And that's how we get the temporary into the thing. Right? Now, we're doing a static cast of like the type trait of the Jekyll type. And is there some overhead in it? And the answer is no. Because what we're doing is we're doing a static cast of like some transformed Jekyll type double parent of an expression. And if the expression is an L value or X value, we cast it to an L value or R value reference. And if it is a PR value, then Jekyll type is a PR value and copy elision keeps it as a PR value. Which means that this entire thing is a no-op. And the only thing we are doing is we are static casting it. In the last case, we're instead creating a TC temporary out of it. But this just creates a class wrapper around the reference. Now, this is, of course, wildly different from this, like without the double parent, because this is C++. So if you just have Jekyll type without the parenthesis, then if it's a non-identifier, it behaves as above. But if it is an identifier and it refers to an L value reference or an object, it casts it to an L value reference. And if it refers to an R value reference, it casts it to an R value reference, which means that this one is stood forward. It's kind of weird how like the syntax difference is like just the extra parent, but you know, that's C++. So anyways, so like the static cast doesn't do anything in the case unless we want to wrap it in a TC temporary. Oh, that was the wrong direction. So to handle a TC temporary, the fundamental rule is a TC temporary must never return from a function, because by definition, it refers to a reference to a PR value created on the outside. So we've got this trait, which handles care of this. If it's a TC temporary, we decay it, otherwise we leave it unchanged. And instead of writing return, we write TC return temporary, which does the decay if necessary. Which means that, like, if we have an object, we write TC return temporary of an L value. This doesn't static cast to an L value, which doesn't do anything. If we move it in, static cast to an R value reference, doesn't do anything, already has that. If we return a PR value, we do a static cast to int, which thanks to copy elision is now up, because it's not a TC temporary. And only if we have a TC temporary, then we do a static cast to the decay and do the operation. So unless we have a TC temporary, this macro is a now up, right? Thanks to copy elision and static cast. Which means that our generic composition can now be written like this. So we call G, we wrap the result in PR value as temporary, likewise for H, pass both to F, and if the result of F is a TC temporary, we need to decay it, so we write TC return temporary. And now it works, because now we've got the information in the type system. Whether F like return reference derived to one of the arguments, because it's a different type than the R value reference. Now, of course, this is still kind of a lot, but we can actually make it even better by realizing that this is generic code. So we're probably not going to invoking the functions directly. We're going to invoking the functions, right? So we can just teach it to our invoke function. We just have to turn it into a macro because we need to like wrap the arguments in TCPR value as temporary, which we can only do outside the function. But then it means that we can just write code like this. We just write TC invoke, and it will automatically call the function with TC temporary if necessary. And then we just need to remember to decay it if the thing got like shuffled out of the boundary. Now, of course, this only works if like F correctly handles TC temporary. Like all projections now need to be aware of TC temporary, because this is a potential reference type that they can be called with. And so like F is a function like our max, which like returns the common reference to our T and U. It must correctly keep the TC temporariness if at least one of the arguments is a TC temporary, because then the lifetime is potentially tied to like one of the arguments, and like we need to handle that correctly. This function always returns the first argument, so it only needs to return a TC temporary of the first argument as a TC temporary, and it can completely ignore what's going on with the second argument, right? Because that doesn't matter for the lifetime. And whereas this function, which always returns a PR value, it must never return a TC temporary because it can never return a reference tied to one of the PR value arguments. And luckily, thanks to like the implicit conversion, in the case of max, we don't need to do anything, right? This code just works, and like we taught TC temporary to like the common reference and stuff, it just follows through, everything works fine, and it will just return it as a TC temporary if at least one of the arguments is a TC temporary. A code like this, however, needs to be adjusted because like TC temporary doesn't have a full member, right? We need to like handle it. And the way to handle it is we need to like temporarily unwrap it. So if it's a temporary, we can like unwrap it by giving us back an R value reference and then just a macro that does the static cast. And so we can implement F by unwrapping the generic temporary and accessing full. But now we just broken our contract because we no longer have a TC temporary annotation on the result. So after we did the unwrap, we need to like rewrap it. So this is the rewrapping code. It essentially says, okay, so we've got some result, and if any of the arguments is a TC temporary, we are going to assume that we need to rewrap it in a TC temporary. Otherwise, we keep it unchecked. And then we just have the convenience macro again. And like, this is a heuristic. This is precisely the heuristic we wanted to avoid with the like TC temporary tracking. But like if you, at the level of unwrap or rewrap, you're like at very specific non-generic code that like cannot handle it otherwise anyway. So we sort of need it at this point to handle it properly. Yes?
On the previous slide, when you have the decal type auto return type there, does the member get returned as a PR value if T is a PR value, and then as an R value reference if T is an R value reference?
So I know that if the like if it's a reference, it gets like the referenceness gets propagated with the member access. So like if you do member access on L value, you have an L value. If you do it on R value, you have an R value, provided you like move it in and like actually have an R value, right?
So if the object's a PR value, would it return foo as a R value reference or a PR value?
I don't know, but it's also not relevant for me to know for this talk because I'm taking it by reference anyway, so it's not a PR value. And so like in this case, it would be an R value reference always because it can't be a PR value, which is kind of my entire problem with the language at this point. Right? So anyways, with this like unwrap and rewrapping heuristic, we can make the logic correct. We like first unwrap it, do the member access, and then we say, hey, if tref was a temporary, rewrap it, please. And so provided f has been updated to handle tc temporary, this is the correct code needed to do our generic composition. Except, of course, there's one complication. Remember when we were implementing max? That was fun times. The complication is that, like, what if T or U is already a TC temporary because we are further composing the composed projection with another composed projection. And then our logic kind of flies out the window because we've got a TC temporary that we don't need to decay because it came from the outside and we haven't created it inside the function. So our actual TC temporary definition looks like this. So we've got this lifetime counter. And so if the lifetime is 0, it's a true temporary and the logic from the previous slides applies. But if the lifetime is greater than 0, it's only a temporary in some parent scope. And then like all the traits handle that by like returning the minimum lifetime of all the temporaries when necessary. And the crucial operation here is like increment lifetime and decrement lifetime. So when we call a function with a TC temporary, we need to increment the lifetime, so it's not treated as a TC temporary inside the function. And then what the function can do its thing, it will not decay it because it's not a temporary of lifetime 0 because it came from the parent scope. And then afterwards we decrement it again, turn it back into TC temporary, and like go on another way. But luckily, this entire logic can be hidden away in invoke. Because this is the operation where we like pass temporaries between scopes. So invoke got the argument conditionally wrapped in like TC temporary zeros if they were true PR values. But if they are TC temporaries from like the outside, then we need to like implement the lifetime, call the function, and then decrement it again. And luckily, with that, we've got an approach that works. Right. Composed projections use TC invoke and TC return temporary and will never return a dangling reference because we successfully tricked C++ into tracking the lifetime for us. And this tracking of TC temporary is accurate, modularly heuristic when rewrapping, which means we do not have any unnecessary decay. The problem, however, is all templated projections now need to be aware of TC temporary, which is annoying. However, that's not actually true. Because TC temporary is only relevant for projections that can potentially return an R-value reference. If a projection never returns an R-value reference, it can never return an R-value reference to a dangling PR value, so we don't need this whole machinery. Right? Only the projections that might want to return an R-value reference need this tracking. Which means that we can implement invoke like this. We first invoke the function with all temporaries removed and check if the result is an R-value reference. And if it isn't, then we don't need to call the function with temporaries. Because the function will not give us an R-value reference. So it doesn't need to be aware of TC temporaries, because we don't need that information to propagate. The result of the function can never be a TC temporary, so we don't need to call it with TC temporary. We only need that lifetime shenanigans if, given the call returns an R-value reference. Then we need to know, hey, where's this R-value reference is coming from? And to do that, we need to then the temporary information so we can properly track that in the type system. And this massively simplifies. So I've glossed over some complication. Like the entire thing works with const, which is annoying and like just adds a whole other mess. It's sort of the fake implementing reference collapsing. So if you've got a TC temporary L-value reference, that should be treated like an L-value reference, because that's how R-value references work too. So we do that. And like if you have an R-value reference to a TC temporary, TC temporary. This is essentially the reference collapsing rules for R values just apply to TC temporary, and we have to like implement them in our type traits. But once that is all done, we're actually using it. Like we are deploying software that uses TC temporary to do that. And TC temporary is in there. It powers a lot of machinery, but like the people that don't work on the machinery aren't actually aware that it exists. It like silently is necessary in the function object in generic code, and it just silently works. all the composed projections automatically handle temporaries, just by using tcreturn temporary. And in fact, since we are like having a macro to like return decal type of something, return that thing, we just treated that macro to do the decay of temporaries. So it's not even the tcreturn temporary, it's barely even necessary because it just follows out of the other macros. We like macros. And like the generic library projections handle temporaries appropriately, but like there isn't a single projection that in like user code, so to speak, that needs to handle temporaries, because almost all projections return never return rvalue reference to begin with, so they don't opt into the whole TC temporariness. And the most common projection is this one, where we just want to get some member of something. And we implemented this one generically via a lambda that creates, like a macro that creates a lambda, which does the necessary wrangling. And so the user code doesn't need to be aware that TC temporary exists. And similarly, we've got a macro for TC member. Yes?
Why does the macro accept multiple arguments?
Why does the macro? It doesn't. It's just that what's considered a single argument in the C preprocessor and in C++ is like wildly different sets. Like if you've got like curly braces and angle brackets, that's like split on the comma, even though it's like, so it like only accepts one argument. Okay. I must say I had like a big headache because people wrote stuff like tcmember.foo function call 42, which broke the entire lifetime tracking, because then the rewrapping logic didn't work because the result was like a function call of something which was a PR value, not the thing, and then it crashed. And so the actual macro now like looks at the stringified expression and sees whether you're like doing something stupid in there, and if so, the macro doesn't compile. But like that's an aside. Yeah.
Sorry.
Yeah.
First, two things. So one, the goal here is to save the decay, right? So you're trying to save performance of the decay here.
Yes.
Is that? Do you know if that's noticeable in any way?
No.
Okay. Second question is, if I want to write my own mux in user code, working in ThinkCell.
Yeah.
At that point, when I'm writing my own mux, then I have to go and do...
Only if you want to return rvalue references. And we've designed the entire thing that you explicitly have to opt into returning rvalue references. Because we don't use decal type auto, we just return some macro, and this macro will compile an error if it ends up being an rvalue reference. So you have to go out of your way to opt into returning rvalue references, because that is dangerous and can potentially dangling. And only in the code that is actually doing it, that is the code that needs to be aware of this. And so like, at this point, you've opted into using rvalue references, at which point you have to do it properly.
Thank you.
Yeah. And like, the motivation wasn't max. I'm just using max because I can do the aside of like the comparison and whatever. The motivation was like some like trimming an array in place sort of thing, and like other stuff. And now I'm also looking at using this whole temporary machinery tricking to like detect whether an iterator is stashing or not, if you know what that means. So like, and like it's useful information to have in the type system. But yes, this is a talk about over-engineering Max. It's not a talk about implementing Max. And like, I didn't, in my defense, I didn't start, like we already had a mechanism to track it, but worse. You have to like essentially separately specialize the trait to say, hey, my function returns a reference to that argument, which broke in some generic places. And so like I was just looking at a different optimization. And like, yes, this entire thing can be avoided by like doing, just decaying the stuff. And then you don't need this entire machinery. But if you don't decay it and you're just doing it without the machinery, you're writing buggy code. Because as soon as you compose it, you go into trouble, right? But like, yes, like what are we even doing here? Right? Like what's going on? Like we're doing something that C++ clearly isn't designed to do well at this point, right? And like, so let's take a step back and like, what would language design look like to solve this problem? So like we've got projections. And like the goal is we don't want unnecessary copies and we don't want unnecessary moves. And like if we compose them, we don't want to return a reference to intermediate temporaries. Like that's what we're trying to do here. And the fundamental problem we have is like, how do we track whether a resulting reference is tied to an argument? Well, we can do it like Rust has that. Like Rust has lifetimes on the temporaries. So you express in a function signature, like this is some like C++ pseudocode, right? Where we say like T reference has lifetime L and U reference has lifetime L, and then the return type has lifetime L. And now we can see in the function signature, hey, we're returning a reference of that lifetime that is tied to either one of these arguments. And then we've got the information we needed, and we didn't need to like invent a TC temporary, right? Because all that the TC temporary is achieving is like getting exactly this, right? By creating this wrapper type, we're passing it to the function, and then we're just looking, hey, function, what are you doing with the lifetime, right? And it's like, I wouldn't say it's a convenient way to do it, but like it's a way to do it. But like this is a more convenient way to do it. By just annotating in the signature, these are the lifetimes of the temporary. And then like Rust doesn't have R-value references, or like so it isn't really, and like move semantics. So like we could say that this hypothetical C++ with like lifetime annotations would just automatically do the right thing. Because like why would we want to return a reference to a dangling temporary? That's just stupid. And if the compiler is able to track that in the open instantiations with the signatures, just decay it, right? Just don't allow the code to return an R-value reference. Like you've got all the information, you can figure it out, just do it, right? But like, I would say this is still unnecessary complexity, right? We have to now annotate the lifetime tracking in it. And so like, why does Rust require lifetime annotations in the signature? Right? Because like all the information, like Rust doesn't have separate compilation, so all the information is right there in the body. Why doesn't the compiler just look at the body and figure out what is the relationships between the lifetimes? And the problem is, and like it requires the tracking is because you don't want to accidentally change that behavior due to some like internal refactor, right? This is part of your contract. Like your contract says, I will only ever return a reference tied to the lifetime of the first argument. And if you then do some optimization, and now we suddenly return a reference also to the second argument, this is a breaking change, right? This would be a silent breaking change, so Rust requires lifetime annotation. But in the specific case of a projection, the lifetime follows from the behavior. Like max is always going to return a lifetime tied to either one of the arguments. A function called first, which always returns the first argument, will always return a reference tied to the lifetime of the first argument. Like if you accidentally changed it, you've broken the contract to begin with. Like for the specific case of like projections where like compute some value derived for some other values, I'd say there isn't any way to like silently change it without also fundamentally changing what the function does. The other thing is, why does C++ and Rust require explicit opt-in to call by reference? Because it has consequences for lifetime tracking. We can't just say, okay, well, we implicitly pass stuff by const2f because like this changes the lifetime and the return type changes, and this has like consequences that we need to be aware of. But like for a projection, there's an obvious choice. Because like when calling max, we don't want to copy the results because that would be stupid. Just do the right thing in this case, right? So like, yes.
Yeah, just a quick question. If I remember correctly, in Rust, you can still see that you call something like with reference on the caller side as well, not only on the callee side, right?
Right.
Okay.
Yeah. So like a better approach would be just say, hey, this function is a projection. And then make everything by value, and like compiler just do the right thing. Like pass it in the most optimal way, return the most optimal return type, and like when you compose it, just don't be stupid. And just don't return a dangling reference to a temporary, right? And like, I would say that like, first-class references are the worst feature C++ has ever added, right? Because it's like so much complexity in function arguments. We've got tref versus tref versus like forwarding references, which is a hack in on itself, right? We've got temporary lifetime extension. Like, who doesn't like temporary lifetime extension, right? Like, we've got dangling references. If you didn't have references, you wouldn't have dangling references, right? And like, the reason first-class references were primarily added was for operator overloading, right? Like the return type of operator square bracket needs to return an L value, right? So an easy way to do that is to just have some way to return an L value. But like this should have been solved differently. And like in particular, like second-class references. Oh yeah, so like so much complexity for everything. Like C++ OX concepts failed among reasons because like references in the signature. And like second-class references or like parameter passing modes are like much better. Just specify, hey, this is an input parameter, not like this is a forwarding reference, right? Just like say what you want, and then the compiler figures out how you want to do that, right? This is a much better solution with just much incidental complexity, right? And that's why I'm excited about Hilo. Because references are the thing in Hilo. You just write the code with value semantics, right? And then it just works. Because the compiler knows how to like properly pass things. And Hyper has subscripts, which are what I'm calling projections. And then it will just do the right thing, it will just do the right lifetime tracking. Like logic, semantically, it's all copies, but like the code gen doesn't do copies, it does the right thing, and this just works. Right? And like this is much cleaner. Like I want this, I don't want the TC temporary mess with the hourly references and the lifetime. Like this is much cleaner. So to conclude the main point and like the question you asked yourself while I was talking about the TC temporary stuff, like, is this all really necessary? And like, if you absolutely want to avoid unnecessary moves, yes. Like you need TC temporary, otherwise you cannot write generic code that like calls stuff without it just blowing up in your face. Right? Like this is a necessary thing if you ever return hourly references, right? And like, if you're fine to like with the unnecessary moves because it gives you so much more simplicity, then yeah, just decay hourly reference. And this is a much simpler solution. But like in reality, like we want different language design at this point, right? Like this isn't an ideal situation. Yeah.
I'm just curious. So I complain to people when trying to do very complicated things in C++.
Yeah.
You looked at just writing a clunked ID check.
Yeah.
How far do you think you could get?
Yeah. So the problem is that this is not about necessarily detecting incorrect thing. It's about doing the right thing in the situation. Like this is the TC temporary. It doesn't cause static asserts. It causes decays in order to do the right thing.
But the lifetime extensions, definitely.
Yeah. So temporary lifetime extensions. We don't use, like we try to avoid temporary lifetime extensions. We don't do it with like clunked ID checks for, I guess, infrastructure reasons. Like this would be like we go some way with like having some more macros. You can do a lot with macros. And like then we just annotate stuff. Like we, instead of writing like autoconstref foo equals something, we've got a macro that doesn't do temporary lifetime extension, and it just gives you an R value, or like a PR value thing with like copies and that sort of thing. So like yeah, you can get a long way with like a static analysis, whether you do it with macros like we do, which isn't necessarily the best way, or like just do it the correct way by writing static analyzers. But like TC temporary specifically is not only about correctness. It's also like it's not trying to like abort compilation. It's trying to do the right thing in the presence of the situation. Right? If you get what I'm saying.
Yeah, just to like further go on that, Clang has the lifetime bound annotation that even in the compiler, not the Clang tiny, will check a lot of these things. This things that like that doesn't help in these situations.
Anyways, I have some more time, so I'm gonna actually go back to like implementing Max for a bit, because you know this talk is a talk about implementing Max. So let's set it aside and work on Max. So this is the code that we ended up with, and like this handles TC temporary implicitly due to the implicit conversion, and it just works, and the magic is hidden away. But of course, like the actual Max function has like a user-defined like predicate that you instead of less. So we also have that. Instead, we just call it best. So best is a function that takes a predicate and two values, and then it calls the predicate in order to figure out what to do with. And so we're calling the predicate in const values, and the TCS const also strips away TC temporary, and always turns it into const ref. And that way, the actual predicate doesn't need to worry about TC temporary. And like it doesn't rely on like implicit conversion. It will just unwrap the TC temporary silently for you, because at this point you don't want to move them in there anyway, so you don't care about that. And then max is just the best of greater, and min is the best of less. Then of course we do this. So if the result of the predicate is true type or false type, we just if const expert short circuit that out, which allows us to do some cool stuff. By like you can have like the best that just looks at like compile time properties of something, and then you can select something at compile time, which is really neat. It's just really annoying that we like have to do the if const expert in there. So I like tried putting that in the macro, like the TC conditional R value one, because like it does stuff anyway. So just teach it that too. By like looking at whatever the condition is, and there was like a compile time constant, just compile time selected, and otherwise do the dynamic selection. The unfortunate thing is because of the if const expert, it requires a lambda. And so when I check that in, a bunch of the other developers that used something called a debugger or something, they complained about an intermediate stack frame in essentially all their code. So I reverted that. Like I want like a const expert ternary or like do expressions or something, so it's not an intermediate stack frame in the debugging. But anyways, with the compile time predicates, we can do stuff like this and say like select the type that has like the bigger size, right? Which in this case would be like it's actually the same size. Bad example, but like we can do compile time selection that is useful in some case. And then of course we make the entire thing variadic. By like doing like looking at 2 at a time and then just forwarding it into the right branch and just do it 3 times, like once at compile time and then once dynamically. And now it's variadic. And you know, that's nice. Anyways, the main takeaway for this talk, every problem in C++ can be solved with more C++, but maybe it shouldn't. Like maybe it should be solved with a different language. And now I'm out of slides. And we're also hiring. So if you like, for some reason, like the TC temporary stuff, and you think like, yeah, I want to work on that kind of thing, like, we're hiring. If you don't, I probably, like as I said, user code doesn't actually care. It's just hidden away in the thing. Yeah, thank you.
He was first.
Yeah, sure.
Have you experimented with, instead of using a TC temporary, like passing explicit template parameters where it would do the R value reference qualified or PR value type that would be visible within the function?
Yeah, that could work too. The problem is that like I don't think you can pass explicit template parameters if you have the function that takes auto and not a template parameter.
Yeah, you can mix them.
Yeah, but like I'm just saying, can you specify them?
May be different, but yeah.
Can you specify auto parameters with like angle brackets when you call it?
You can. It's just the order that they appear auto in the parameter list gets appended to the end of the explicit template.
Oh, okay, I didn't know that. So yeah, that might have. I mean, it would break for lambdas because then you have to like dot operator.
Yeah, the dot. Yeah.
Yeah, so that's a non-status because yeah, like because like the TC member, that's like 99% of all projections.
But so is the macros with the TC temporary is pretty awful too. So.
Yeah, but you know they work. Yes.
So I know it's a lot of clicking, but can you get back to TC temporary?
Dang it! I don't actually see that.
Yeah,
3
so
clicks.
I don't quite understand how you solve the problem with lifetime here, because you take this U by value and then assign it to reference, and in this case you have a lot.
Yeah, so this is slide code. I simplified it so much.
We should read it as an idea, right?
Yeah. So the idea is we've got one constructor that takes an lvalue reference and one constructor that takes an rvalue reference.
Okay.
Sorry, I simplified it too much. Yeah.
Yeah, I mean, it's like you're saying about like lifetime, and you might create a wrong impression that it also somehow prolongs lifetime.
No, it doesn't pronounce that. Like it keeps it as an rvalue reference, and the only way this works is because of temporary lifetime extension in the function arguments when you like turn a PR value into an R value. And like this entire thing is like meant to live like within a sub expression, and so everything works out. And like once you go out of the sub expression, you have to like return this thing as like
If that's okay, I'd like to go back to what I was trying to ask previously.
Sure.
So you said that alternative where Rust's lifetime annotations would be okay for you instead of temporary.
It's essentially the same thing.
But they do. I don't know Rust, but
Yeah.
it seems like they do different things. It seems like Rust lifetime annotations would prevent you from compiling.
Yes, yeah. So like Rust as a programming language doesn't have R-value references. So it doesn't have the entire concept of like returning an R-value reference from a template. It would always move essentially. And this is like a problem in Rust code where like essentially you like when you like create like something on the heap, you have to like create a literal on the stack and like mem copy it into the heap and stuff like that, because it doesn't do the sort of R-value reference handling. So what I'm saying is like a hypothetical Rust-style C++, which would be a horrible language, but like it would solve this problem by like taking Rust lifetime extension, combining it, lifetime annotations, combining it with rvalue references, and just adding some way to like have the compiler prevent the return of an rvalue reference thanks to the lifetime annotation.
Okay.
Right? Because in Rust, the max function would always like return the lvalue reference, so to speak, and so that's how they solve the problem. They essentially have like the const gref code, right? That I started with earlier, and I don't think they do a mixed comparison. And if they were to do mixed comparison, then they would return it by value, and then you would always do the mem copy, which is Rust's move. So like Rust prefers moves over that sort of thing. Does this answer your question? Or?
Good enough. Thank you.
Yeah.
I had a question. I was curious. Isn't qualifying the member function with const makes all its members const? So returning a reference to a const. Shouldn't that be returning const reference for the conversion operator?
The conversion. So the temporary stores a reference. So the constness of the TC temporary doesn't matter, because if it stores a mutable reference, it will always store a mutable reference. And
then you can just return a reference to that.
Yeah, yeah. Okay. And then you like don't return you return essentially the reference by value, but like
that's interesting.
Yeah, okay. Yeah. Anyways, I had a lot of fun with this. That's cool. Yeah. Any other questions? Any more people want to complain about this thing? You know, it solves the problem. So.
I think we knew what we were getting into.
I
think we knew what we were getting into.
Yeah, I hope I made it clear. Yeah. You should have went to pragmatic CMake if you wanted something better. Which is like the polar opposite of this talk, I think.
Would you try modifying compiler and kind of implement these as the first class?
Yeah, so like we're using MSVC as our main compiler because like PowerPoint and Windows. And like I want to move to Clang on Windows to like make this work. But like I feel like this is going to be a slippery slope because soon then we're just going to have a fork of Clang.
Yep.
And then, so maybe it's good that we still use MSVC and can't actually hack our stuff into the compiler. Because the code we write is still technically C++.
Part of your talk reminds me of, not sure who it was, but the talk title was C++ lifetime disasters. And it was kind of...
that's by members.
Okay. Yeah, so same ideas.
Yeah.
So, is temporary something that like users in general are going to be writing to wrap to pass in, or is this entirely in?
This is entirely hidden away.
Okay, good.
The invoke creates the temporaries, and then the like decal type return macro does an implicit return of temporary, and this is entirely hidden away. The only way that like shows up if you like opt into returning an rvalue reference, then you will suddenly need to handle it, and if some like code breaks, then like it shows up in the compiler error messages, which isn't nice, but you know they weren't nice before, so
Because the thing that generally scares me about this is you have an object type that you claim is kind of reference-like, but auto of it is not a reference.
So like that's also like where we have an auto cref macro that handles it correctly, and also prevents temporary lifetime extension. Because like if you have decal type auto and then you have auto cref and you return it and temporary lifetime extension like that. So like we used this macro to begin with anyway. So it was actually very easy to just hook that into the various macros that interacted with it. Like the surface level impact of this was like surprisingly small. Once I realized that, once I did the like if context band and right, then the surface level impact like it was essentially just like a couple of files in the core library needed to like be aware of TC temporary and the rest of the code. More than all the bugs where people use the macros wrong. But like that was. Like I'm not saying you should do it. I'm just saying you can do it.
You're saying you should come to SyncCell to work and to do it.
Yeah, that works too. Like take this and then like implement it to detect iterator stashing. That would be really neat.
So I think it's an error to return a reference to a local from functions in C++ 26.
I mean, Yeah, but like you can hide that sufficiently that it's no longer an error.
If you take an R value reference, could you also return that from function?
Yeah. So like C++26 made it an error if you have like int x, return x, and the function returns a const reference, for example. Then that is an error. Because
It's an error to even return a const reference.
I mean, I'd hope so.
I don't know.
I think there was something like that prevented it. The problem is if you no longer write return x, but return f of x, and f is the identity function, then the compiler doesn't know that it's the identity function, right? Because it doesn't do lifetime tracking in the signature. So then you need some way to like track lifetimes in the signature, you know, to like know that this is a
Trust.
yeah. Or you know, just don't do references. That's all. I hope I sufficiently annoyed you.
That was awesome.
Yeah, that was cool.